In the rapidly evolving world of LLMs, standard retrieval augmented generation, or RAG, has become our default. But as we push these systems to handle highly complex, multi-step reasoning, standard RAG reveals a fatal flaw. It operates strictly as a stateless, simple dictionary. It uses vector embeddings to retrieve isolated fragments of text, but it completely lacks the human brain's ability to dynamically connect the dots. These traditional methods leave us with a fragmented understanding, creating a severe bottleneck for machine intelligence. To solve this lack of associativity, researchers turn to structure-augmented methods like knowledge graphs. But as we look at the data in Figure 1, they discovered an embarrassing and unacceptable compromise. While graph-based methods vastly improve narrative understanding, their performance on basic factual memory drops significantly. It's the equivalent of teaching an AI to master advanced calculus, only to realize it has forgotten how to do basic multiplication. This creates a painful dilemma: you can have strong recall using vectors, or deep logic using graphs, but not both. Enter HippoRAG 2. To fix this broken paradigm, the researchers looked directly at the human brain, specifically, how the hippocampus and neocortex interact. HippoRAG 2 introduces dense-sparse integration. During offline indexing, it treats abstract concepts and entities as sparse coding, the phrase nodes. But crucially, it preserves the raw, original context as dense coding, the passage nodes. During online retrieval, it uses an LLM as a recognition memory to actively filter out irrelevant triples before running a personalized PageRank algorithm. It retrieves, it filters, and then it connects. The results of this bio-inspired approach are absolutely crushing. Looking at the QA performance, HippoRAG 2 achieves the highest average F1 score across all benchmarks, hitting 59.8. But the real story is in the specific breakdowns. Previous graph methods sacrificed facts for logic. HippoRAG 2 refuses to compromise. In complex associativity tasks, it outperforms NV-Embed v2, a massive 7 billion parameter embedding model, by a staggering 7% margin. So, what is the secret sauce driving this? The Ablation studies in Table 4 give us the exact answer. If we remove the passage node, the dense contextual coding, the average recall drops from 87.1 to 81.0. Context is undeniably king. Let's look at a real-world multi-hop example in Table 6. While standard models fail, HippoRAG 2's recognition memory successfully isolates the triples to literally connect the dots. But the ultimate test of any memory system isn't just a static benchmark, it is time. What happens when the database grows? Figure 3 shows a simulated continual learning environment. As we push the corpus towards 100% capacity, traditional retrievers like NV-Embed v2 start to degrade in complex tasks. They get lost in the noise of their own vectors. While HippoRAG 2 also degrades slightly, it maintains a remarkably consistent lead over vector models. It proves that this architecture is a viable, scalable path toward true nonparametric continual learning for AI. We are witnessing the evolution of machine memory into something that closely resembles human cognition. Thanks for watching.